Good afternoon. Today is Thursday, April 23. This is the lesson for that day, and let's see, I do have a couple of announcements. One of them again is that last day to withdraw is Sunday the 26th. And then the other announcement is that with this video, and the handouts that come with it, you should also be getting the handout for quiz 4. That quiz 4 covers through 6.5, which we will finish today. We have a couple more problems left to do on 6.4. We'll get all 6.5 done, and we'll look at 6.6 as well. So again, you should have those handouts, and you should also have the handout for quiz 4, which is due on Tuesday. So we won't see each other again until Tuesday's class next week, which means that make sure that you have it done and a clear photo taken and sent as an attachment through Canvas to me by the deadline, and the email that came with this will remind you of that deadline as well. So I think that's my only announcements, so I'm going to erase that, and we're going to go finish 6.4, which we left off with a few problems left to do from last Tuesday's class. So let me get rid of this. And we are almost done with 6.4, where we were discussing the idea of logs and what they are. And again, what is a log? It's just another way, or by definition, of an inverse function of an exponential function. So in other words, log functions and exponential functions are interrelated. The one is the inverse of the other. And in fact, I can write log equations in exponential form and exponential equations in log form. And that will become useful for me when I talk about trying to solve log equations or even exponential equations that we can't make same bases for. So we are on the flip side, and we are ready to do number 5, I believe. And this one, so there's a hint here. It says to rewrite it in log form. This one is not a log equation. It's actually an exponential equation. The unknown is in the exponent. And one way that we know to try and solve those, which we will always try, is to try and make same bases. And if I can make same bases, then I can drop the base and equate the powers. But this base is a base of e. And again, e is a number, not a variable. And this is a base of 8, which I could turn into a base of 2, which is not a base of e. So I have an issue here. I cannot create same bases, and we haven't learned a way to solve something where we can't create same bases. But in fact, and this isn't how we'll do it in the next section, but in fact, exponential equations and log equations are interrelated. I can write one in the other form. So what I'm going to do here is I'm going to play with this, since I don't have any better way of doing it, and rewrite this in its equivalent log form. And if I do that, what I have here is log, I leave space for a base and an argument, equals an answer. The base of this is the base of the log, so this is log base e. It's e to the power of 3x plus 4, so that 3x plus 4 comes over here. And the answer is 8, which means the 8 is the argument. So this basically says, rewritten in log form, log base e of 8 equals 3x plus 4. Or in other words, what's another way we can write log base e? That's just natural log. So this is natural log of 8 is equal to 3x plus 4. What kind of an equation is this? Well, where's my unknown? It's right here. This is linear. So that means I can solve this. For x, I need to subtract 4. Natural log of 8, ln of 8, is a number. It's a constant. It's also going to be irrational. I'm not going to approximate it yet, because the directions on this one will be give me the exact answer and then give me the approximate answer rounded to I'm going to say we're going to round this one to 3 decimal places since that's how I did it in my notes. So what happens here is I can't combine these because they're not really like terms the way they're written. So this is ln of 8 and then minus 4. So understand the 8 is the argument of the ln. The 4 is not. I'm just subtracting 4 from whatever this is. And that gives me 3x. And now I'm going to divide by 3. And this time I actually am going to divide the whole side by 3 because this is all a constant. And so I'll just take whatever that gives me and divide it by 3. So this gives me x. And so maybe I'll write it normal now. So this is x equals whatever ln of 8 minus 4 all divided by 3 is. This is my exact answer. Okay, I haven't taken anything and rounded it. Unfortunately, it's a little bit meaningless to me because I need to figure out what ln of 8 minus 4 gives me and then take that answer and divide it by 3 in order to get an approximate answer. But this is the exact answer for x. If I want to get the approximate answer, I'm going to take this and put it in my calculator. And so now I'm going to go let you do that. So get out your calculator and tell me what you get when you take ln of 8 minus 4 and divide it by 3. And we'll compare answers. So I'll give you a teensy bit of time to do that so you can pause me for a second and figure it out. And here's some answers I'm getting from you guys as you raise your hand or shout out an answer to me. I have one answer. Some of you got 0.462, rounded to 3 decimal places. And some of you got 1.897. I'm getting a bunch of different answers here. That's never a good sign. Some of you got 0.746. So did any of you get, some of the rest of you get these answers and you just weren't willing to raise your hand and admit it? Well, if you got any one of these answers, you need to go try again. So I'm hoping that some of you got negative 0.640. Negative 0.640. It said specifically to 3 decimal places, so I had to include that 0 there to show that I actually rounded it to 3 decimal places. So this is actually what x is for my approximate. So this is my approximate answer or solution. So all those incorrect answers over here that I listed that some of you got, what are you doing wrong when you put this in your calculator? So when you put this in your calculator, you need to respect order of operations, which means that, so in the calculator, so you typed in, you used your ln key, and it came up and put a parenthesis for you, and you wrote down 8, and then you wrote down minus 4, but you never closed the parenthesis. So if you do it like that, then you're telling the calculator that the argument is actually 4, because it's going to take 8 minus 4 and get 4 for the argument, which is not what you want. You want the argument, you need to tell the calculator the argument is 8, so close the parenthesis. And then you hit minus 4, so maybe you did that, and you thought, I did it right, I did that part right. And then you wrote divided by 3, and then you hit enter. Well, now there's still an issue here, because order of operations is going to go figure out ln of 8, and then it's going to take 4 divided by 3, or it'll do that first, but nonetheless it'll still figure out ln of 8. 4 divided by 3, is that really what you want to have it do? Take 4 and divide it by 3 and then subtract that answer from whatever ln of 8 is? That's not what this is telling you to do. This is saying we want to figure out ln of 8 minus 4 first and then divide it by 3, so you're going to have to, if you're going to do it all in one shot, you're going to have to put parentheses around the entire numerator so that you figure that out and then divide it by 3. Otherwise, if you take ln of 8, close the parenthesis, minus 4, and then hit enter, that's okay. Don't write that answer down. Don't round it yet. Take it just exactly the way it is, and then divide it by 3, and then take that answer, write it down, and round it to 3 decimal places. So again, rounding is only at the very end. Do not round in the middle of a calculation because you want to write the number down. Don't do it. You need to either do it all in one shot or just keep going and because your calculator will store what you've got, and then if you divide it by 3, it'll take that storage and divide it by 3. So this is the proper way to put it into your calculator in order to get that answer. So we're ready for number 6. See what we can do with it. I have room here. Number 6 again says solve, and when I look at this, what I see, it's not a log equation again, I threw a couple of these in here. I see that this is exponential again. And the base here, oh gosh, this is messing me up. See that 8? Because the base looks like 10. So here's my first question to you. Can I just turn that into 80 to the power of 2x minus 7? I'm hoping to see a whole bunch of heads shaking. No, you can't do that. In order to multiply bases, it needs to be the same base. Multiply same bases, keep the base, add the powers. These are not same bases. Could I turn the 8 and the 10 into same bases? No, I could turn 8 into a base of 2, but that doesn't do me any good because 10 is 10. It's not going to change in terms of its base. So this 8 is in the way. I can't really combine it with this, and in order to use the idea of an exponential equation of trying to create same bases, I have to have just the base here. I need to get rid of this 8. So how can I get rid of this 8? What's the 8 doing? It's multiplying. So how do I get rid of it? I will divide. So I'm going to divide both sides by 8 to try and see what I've got going on here. So this becomes just 10 to the 2x minus 7 equals 3 divided by 8 is 3 divided by 8, 3/8. Don't turn it into a decimal and round it. Never, ever, ever round in the middle of a calculation, ever. Or in the middle of solving an equation or a problem. So this is what this now says. Well, now I can see clearly it is exponential. The base here is 10. And this base, so to speak, is 3/8. Am I ever going to be able to create the same base for these two? I don't think so. So now we haven't learned another way to do this other than I do know that exponential equations are related to log equations, and I can rewrite one in the other one's form. So since this is an exponential form, I could try rewriting it in log form. And again, like I said, once we get to the next section or the section after that, we won't do that anymore because sometimes it can be a little more difficult than it needs to be. But that's what I'm going to try and do here. I'm going to rewrite this in log form for good practice. So this says log, I leave space for a base and an argument. The base of the log is going to be 10. It's 10 to the power of 2x minus 7, so the 2x minus 7 is over here. And the equals 3/8, the 3/8 is going to be my argument. So this says log base 10 of 3/8 equals 2x plus 7. Well, first of all, there is a shorthand way of writing log base 10. Log base 10, we usually don't put in the base, and we just write log of 3/8, which means I can use my calculator key on this, which is good. This is a constant. It's an irrational number, but it is a constant that I will be able to figure out for an approximate answer, but not yet. They want the exact answer, and then we'll approximate. Never approximate in the middle of a problem. So do not go figure this out and write something down to 3 decimal places for it. Not yet. And over here, I've got 2x minus 7. This is linear. So I'm going to solve my linear equation. I'll add 7 to both sides. So I've got log of 3/8 plus 7 equals 2x. And then I'll divide by 2. And I'm going to divide the entire side by 2 because, again, this is a number. And so I don't really need to divide separate pieces by 2 because it's all just a constant. So that means my exact answer is x equals log of 3/8 plus 7 all divided by 2. There's my exact answer. It's meaningless other than it is an exact answer, and if I had to calculate things on an Excel program, I would use this and then plug in whatever it is and let it approximate it, or do it on my calculator, which is what I'm going to have you do for my approximate answer. So when I do my approximate answer here, again, I'll let you put this in. I'm not going to completely go over how this should be entered, but I'm hoping you get the idea. log of 3/8, that has to be in parentheses, plus 7. Either hit equal and then divide by 2, or embed all of this in parentheses as well and divide by 2, just like we did the other one. And when you get this one and you approximate it and round it to 3 decimal places, you should be getting x is approximately equal to 3.287. So this is my approximate answer rounded to 3 decimal places. So we've got 2 more of these, and these last 2 are actually log equations. So notice I didn't have to worry about checking those because the original equation was not a log equation, so there were no restrictions on my answers. So this one, they say solve, and it is a log equation. So that means I'm going to have things to think about in terms of restrictions. So I'm just reminding myself now, I know what the base is, so I don't have to worry about that. But remind me again about the base. The base of a log needs to be greater than 0, not equal to 1. Okay, don't have to worry about that. The argument, so that's where the x is in the argument. So I am going to have to be careful here. The argument of the log needs to be greater than 0. So when I get my answers, I'm going to have to make sure that I am keeping the argument greater than 0. All right, so here we go. Log equation, single log, numbers on the other side. I can rewrite this in its equivalent exponential form and then see what kind of an equation I have. So if I do that, this says 5 to the power of 2 has to equal x squared plus 1. 5 to the power of 2 equals x squared plus 1. What kind of an equation is this now? Looks quadratic to me, and it looks like the square root property will work nicely on this one. I just need to get rid of the 1 and understand that that's 25. So this is 25 equals x squared plus 1. I'll subtract 1. I'll get 24 equals x squared. I'll take square roots of both sides, plus or minus. So I get x is equal to plus or minus, and I'll simplify this if I can. So there's a 4 times a 6 in there, right? So the square root of 4 is 2. So plus or minus 2 square roots of 6. That's x. But before I circle it, so there are 2 answers here, and before I circle it, I need to make sure that my argument will be greater than 0. So argument, so check. Argument greater than 0. So now I know you look at that and you go, oh, I'll just get rid of the negative answer. Don't do that. You need to actually look at the argument. The argument may be more than just x, and in fact it is. So in other words, argument is x squared plus 1, right? So when I plug in the positive 2 square roots of 6, and I square it, and I add 1, will that be greater than 0? Well, I think so. So this is just going to give me 24, and 24 plus 1 is 25, and sure enough, that is greater than 0. So that one works. Now, you were tempted to get rid of the negative 1, right? So let's try it. What happens if I put negative 2 square roots of 6 in here? Well, if I put negative 2 square roots of 6 in the argument, and I take it, I square it, and I add 1, is that greater than 0? Well, what happens when you square negative 2 square roots of 6? You end up with a positive 24. And 24 plus 1 is 25, and that is greater than 0. So guess what? Both of these answers get to stay because they both work. They both create an argument that's greater than 0, so there's not an issue with having a negative answer there. So be careful. It's not just because you have a negative answer that gets rid of it. It has to do with if that negative answer causes an argument that's not greater than 0. That's where the issue comes in. And I will tell you that if you're solving a log equation and you get an answer and you either forget to show me the check or So or you just don't do the check at all, you're going to lose points. So in other words, you're going to have to show me that you took the time to check and make sure that the answers work for the argument, or maybe some of them don't work and you're eliminating them. And then the last one, assess this. This is a log equation again. I'm going to make a note. This time the unknown is the base. And again, the base needs to be greater than 0, not equal to 1. So I'll have to be careful with that when I get my answer or answers for this. So single log, not a log over here, which means that I can rewrite this in its equivalent exponential form. So I'm going to write x to the power of 4 has to equal the 81. What kind of an equation is this? Well, this is a quartic equation. In other words, there are 4 answers here, and I need to go find all 4 and then see which ones I'm going to keep. 4 answers here. So how do I solve this? Do not take a 4th root. I need to find all 4 answers. We don't have a rule for a 4th root. We do have a rule for a square root. So I could do a square root, or I could bring this over here and start factoring. I know most of you like the idea of just, y factor if I can just take square roots. So be careful with that. So I'm going to take a square root property, plus or minus square root. Square root of x to the 4th is x squared. Plus or minus the square root of 81 is 9. So what I now have here is I have either x squared equals 9 or x squared equals negative 9. Now I'm going to solve each one of those because they are quadratic. I'll get 2 answers here and I'll get 2 answers here. That's where my 4 answers are coming from. Square root property again. Square root plus or minus square root. So x equals plus or minus 3 from that one, or square root property again. Square root of this guy plus or minus square root of this guy. This gives me x. This gives me what? Plus or minus. What is the square root of negative 9? 3i. So there's my 4 answers. 3, negative 3, 3i, negative 3i. So now let's talk about, it's not the argument this time, but it's the base. I need to check the base, which needs to be greater than 0, not equal to 1. Well, neither one of these are 1, so that's taken care of. Now I just have to check greater than 0, and what is the base here? The base is just plain old x. So plain old x greater than 0, not equal to 1, which again, we kind of have ruled that out. So 3, is 3 greater than 0, not equal to 1? Yes. Is negative 3 greater than 0, not equal to 1? No. So it's gone. That guy's gone. 3i, is 3i greater than 0, not equal to 1? Well, no, it's imaginary. So it's not even a real number, so no. And is about negative 3i? No, it's imaginary again. So no, it doesn't work either. So this is completely gone. So what's my only answer here? X is equal to 3. X equals 3. Only solution to this one. So again, I need to see that you checked it though, and that you're thinking about what are the restrictions on my answers here. So that finishes 6.4. We're ready to move on to 6.5. So let me get rid of the board and switch over. 5, you'll notice, is entitled Properties of Logarithms. This actually should be a review. You should have done all of this in intermediate algebra. Yeah, all of this should be a review. It's possible that one of these problems might be harder than what you got in intermediate algebra, but probably not. So this should be a total review. I've listed the important properties of logs, and we'll just review them quickly. So I remind you that the base of the log has to be greater than 0 and not equal to 1, and the argument of the log needs to be greater than 0, so I'll keep reminding you of that. This first property basically says that if you have a log of any base, and it's a log of 1, you're going to get an answer of 0. So if you think about that, so basically it's saying log base 10, log base 2, log base 5, log base, whatever the base is, it's legal, of 1, where the argument is 1, is always going to give you 0. And you can put log base 10 of 1 in your calculator, so log of 1, and it will spit out 0. And the reason for that is if you write it in exponential form, a to the 0 power is going to equal 1. In other words, any number other than 0 to the 0 power will give you 1. And so that's always going to be the case. So it's a good one to remember. Log of 1 is 0, no matter what the base is. The next one talks about where you have a log of a base, and the argument is the same, the base of the argument is the same as the base of the log, and then you have it to some power, whatever that power is. These are inverse functions. Actually, what's going on here is that we have an exponential function stuck into a log function. And remember, exponential and log functions are inverses of each other. That's how we define the log function. So when something like that happens, you get back to x, which is actually whatever that power is sitting right there. And I wrote down the reasoning. If you use the circular logic of taking the base to the power of the answer equal to the argument, you get a to the x equals a to the x. A to the power of x equals a to the x. And so I can kind of see that happening. And what this is saying is this. So as a concrete example, if I write down log base 2 of 2, you should be able to tell me the answer here. This follows this logic. If the base of the log is the same as the argument's base, and there's a understood power here of 1, this should give me whatever that understood power is. This should give me 1. In other words, 2 to the power of 1 gives me 2. Or if I wrote log base 3 of 3 to the 4th, the fact is since this base is the same as the base of the argument, the answer is whatever that power is right there. So this would be 4. In other words, 3 to the 4th equals 3 to the 4th. So I can kind of see it happening. It's a very powerful property. We'll use it a lot. Sometimes we use it by itself, or we let property 6 help us a little bit, depending upon what we're used to doing with these. But really nice property, and it kind of gets the job done quickly in terms of figuring things out. And in fact, I'm going to do ln for a second. So ln of e, remember the base of ln is an understood base of e, so this should be 1, and that will always be the case. This is a big one to remember, because remember, there's an understood base of e here. E to the power of 1 equals e. In other words, there's an understood power of 1 here, and that would be my answer to that. Same thing with natural log of 10 is going to be 1. Again, there's an understood base of 10 here. 10 to the first power equals 10. So these are really nice ones to remember, particularly that ln of e is equal to 1. That gets used a lot. Rule number 3 says that, so rule number 3 is a little weird. It says if I have a base to a power of a log that has the same base, and the argument is x, this is just going to give me the x. Well, this is sort of the reverse of this logic. Again, log functions and inverse function, log functions and exponential functions are inverses of each other. So if I put one in the other, I should get x back. And that's what's happening here. I'm taking what used to be a to the x, and in place of the x, I'm putting in its inverse, which is log base a of x. and they undo each other. And what I wrote down for the reasoning here is I said because log base a of x is equal to log base a of x. Well, I know that, yeah, obviously, right? They're the same thing. How does that explain this? Rewrite this in exponential form for me. A to the power of log base a of x, a to the power of log base a of x equals x. So again, because of the fact that log functions and exponential functions are inverses of each other, if I put one function in the other, composite functions, I should get x back, and that's exactly what's happening here. Let's see. So rule number 4 says, so 4, 5, and 6 are really, really useful as well. So again, I tried to write down the really useful properties here. Rule number 4 says if you have a log of a product, and this is called the product property. I'm not going to prove these, but I'll kind of relate it for you. If you have a log of a product, you can split this up into 2 single logs where the factors of this product are the arguments of each log, and you add them. So this is the log of the first factor plus the log of the second factor. And the property that's related, or the property I can relate this for with exponents, if you multiply with exponential rules, if you multiply same bases, you keep the base and add the powers. And that's why these are adding. This is multiplication, and it's turning into addition of separate logs. So there's again a relationship between exponential rules and log rules. The 5th rule is what happens if you have a log of a quotient, so log of x over y, and if you have this, then it's the single log of the numerator minus single log of the denominator. Why is that happening? It's called the quotient property. The fact is that when you have same bases dividing, with exponential rules, when you have same bases dividing, you keep the base and subtract the powers, and that's what's going on here, and it's always the numerator power minus the denominator power. So that's the relationship here to maybe help you to remember the rules. So this is you add the logs, this is you subtract the logs, log of the top minus log of the bottom. The 6th rule is also a very powerful rule, and it says if you have a log of a argument that is a base risen to a power, you can actually rewrite this, which is why I said there's sometimes other ways to do these sorts of problems. I can rewrite this as r multiplying with log base a of plain old x. In other words, this power can come out as a multiplier. And this one is called the power property, and it is related to the idea with exponents where you have, if you have a base to a power and then you raise it to a power, so a power raised to a power, then what do you do with the powers? You multiply them, and so that's what's going on here. This can come out as a multiplier in front of the log. Very powerful property as well to help me rewrite things. And the last really useful property is what's called the change of base theorem. And remember, we said in your calculator, if it's not log base 10 or ln, which is a log base e, you can't use your calculator, which makes life a little difficult if I'm trying to get an approximate answer to something. So this is a really powerful property. It says that if you have log base a of some argument where a, the base is not 10, or e, so you can't use your calculator, then you can rewrite this as log of m over log of a. So look what they did here. This argument is still the argument, but notice the base here, since I didn't write it in, is base 10. And over another log, and this log's argument is the base of the log, and the base here is 10 again. So it's log base 10 of m over log base 10 of a. So powerful, powerful property. So I skipped the very first part of log base b of m over log base b of a, because the fact is I don't want any other base other than 10 or e. So I skipped that one and I just wrote this. I could also do it log base E, which in other words is ln of m over ln of a. I should get the same answer. Believe it or not, change of base theorem. Very, very powerful. So we're going to do some problems using these properties. We're going to do different things using the properties, get a little bit of practice. This is the new stuff. Well, it's not really new. It should be a review. So let's go try all these different examples and see what we can do with them, trying to make use of all of these properties. So these first two examples say find the exact value using the properties, no calculator. So they don't want me to approximate anything. They're basically saying just get an exact value, don't put it into your calculator. And here's what this first one says, log base 3 of 8 times log base 8 of 9. And they want me to figure this out without the use of my calculator. Which worries me a little bit because, again, if I look at this, I can't really see one of the properties 1 through 6 that help me much because I don't have a same base as an argument here where I can figure things out. Or even if I'm thinking 3 times what power will give me 8, I would have to approximate that. And same thing here, there's no good property in the first 6 properties that help me with this. 8 to some power equals 9. I can't really use the first 6 properties, but I'm thinking, all right, well, my only resort here is to think about property 7, which is the change of base theorem. So I could rewrite this first one as log, I'll just keep base 10 here, log of 8 over log of 3, both base 10. So I'm leaving off the base 10. This is the change of base theorem. So that's this one. Still not sure how that helps me, but I'm going to keep going here. Times, because presumably this can be done, so this is my only shot, I think. I'm going to use change of base theorem on this one. This is going to be log of 9 over log of 8, both base 10s. Now I see a little bit of something going on here. When I multiply these two, I can cancel these guys. Look at that. That's nice. So this leaves me with log of 9 over log of 3. Well, now I'm still not, because these are both base 10 now, and they don't want me to use my calculator. They want an exact answer, and they're kind of giving me the impression that it's not going to be irrational. So I'm going to keep trying here. I'm going to use the change of base theorem back. So this comes from a log base 3 of 9, right? Log of 9 over log of 3. So now take a look at this one and think about this one. I might see a relationship here. In other words, 3 to what power will give me 9? Or in other words, what we did before is we said, all right, let's let that be x, and now I'll try and solve it. 3 to the power of x has to equal 9. I can create same bases. 3 to the power of x equals 3 squared. Drop the bases, equate the powers. So that means that log base 3 of 9 is equal to 2. So log base 3 of 9 equals 2. So that means this original thing is equal to 2. So there's my final answer. I never used a calculator. You could go put, well, you can't really put that in the calculator, but you could put this in the calculator, or I suppose this times this in the calculator, although that kind of cancels, so it's not that difficult to put it into your calculator and check it. So just manipulating things using these properties and seeing if we can get somewhere. And the second one, oh no, this one looks weird. This one kind of looks like, which number was it? Number 3, where I have a base and then I have logs up here in the power, but I've got too many logs up here. Rule number 3 just says a single log. Well, guess what? I can use property number 5 and turn this into a single log. And in fact, that's usually what we like to do. We like to take a bunch of separate logs and combine them, condense them into a single log. So if I write this as a single log, it's both base 4, so log base 4. What's going on with the argument? Well, it's minus, so this is going to be 7 over 3. So what this says is 4 to the power of log base 4 of 7/3. Now it looks like property number 3, which says that if you have a base and then to a power of a log that has the same base, then whatever that argument is going to be your answer. So this guy is equal to 7/3. So we used a few properties on that one. Now we're going to go look at 1 and 2 underneath the first set of 1 and 2. And this has a new set of directions. It says use the properties to rewrite in terms of A and B. Oh boy. Where A is equal to, where ln of 2 is equal to A, and ln of 5 is equal to B. So I put these on here because there's a couple in the homework like this, and it really makes you think. And so here's what they're telling me. A is ln of 2, and we're letting B represent ln of 5, and they want me to rewrite ln of 2.5 so it just has A's and B's in it. Just has A's and B's in it, which means it has to be made up of ln's of 2's and ln's of 5's. Well, I see a 2 and a 5 there, but it's a 2.5, not a 2 plus a 5 or a 2 times a 5. So I'm trying to figure out how I can rewrite 2.5 so it ends up with just a 2 and a 5, either with the 5 and the 2 subtracting, or the 5 and the 2 multiplying, or the 5 and the 2 dividing, or something that I can use one of those properties. So when I really think about this, convert 2.5 for me into a fraction. So 2.5, that's 2.5, right? Which is 5/2. So now take a good look at this. This is the quotient property. This turns into ln of the numerator minus ln of the denominator. So ln of 5 minus ln of 2. And guess what? Ln of 5 is B minus ln of 2 is A. And there we did it. We wrote it in terms of A's and B's only. It's a little bit weird, but still just trying to get you accustomed to the properties a little bit. And then this last one, I'm going to get rid of. So still using ln of 2 equals A and ln of 5 equals B, can I rewrite the second one in terms of A's and B's? So let's see, it says ln of the 4th root of 10. Well, I know 10 is made up of 2 times a 5, for what it's worth, but this is messing me up right here. And in fact, when you have logs that have radicals, in terms of expanding them or condensing them according to the properties, you want to rewrite this without the radical, always. So I'm going to first rewrite this as ln of 10 to the what power? 1 over 4. So 10 to the 1/4 power. And then that property number 6 comes in really handy here. I can rewrite this as 1/4 times the ln of 10. Really useful to get rid of that, because now how can I rewrite 10 using 2's and 5's? I can rewrite this as 1/4 of ln of 2 times 5, right? Where the argument is 2 times 5. But now property number 4 says you can rewrite this. So this piece I'm going to rewrite. This 1/4 is multiplying with this. So I think I'm going to turn this into 2 logs. So I'm going to put parentheses here. This is going to be ln of 2. plus ln of 5. So in other words, log of a product can split up into two separate logs, the log of the first factor and then the log of the second factor added. And what do we know about ln of 2? ln of 2 is A, ln of 5 is B. So there it is, writing with A's and B's, or you could say 1/4 A plus 1/4 B, but I'm just gonna leave it like that. So now, we did a few kind of strange problems manipulating with the properties. What's more normal are the next 6 problems, which are trying to get us used to going from a single log and expanding it into a bunch of sum and differences with logs using the properties, or, so that's like number 1 and number 2 and number 3, or like number 4, 5, and 6, where we have a bunch of single logs and we want to actually contract a bunch of separate logs, and we want to actually contract it into a single log. So sometimes we go from one log and we expand it into a bunch of separate little logs, or we have a bunch of separate little logs and we condense them into a single log. Honestly, what do we use more often? 4, 5, and 6, where we have a bunch of logs and we want to actually condense them into a single log, because that will help us be able to solve log equations. But we're going to practice in both directions using the properties. So we're going to go look at number 1 here and see what we can do with it. So 1, I have a single log. So the directions would be expand it. So use the properties to expand this into sum and or difference of logs. So this is a single log and I want to expand it. Not normally the direction we like to go in, but it gives us a little practice with the properties. So this is a log, a natural log, but that just means log base e. This is a log of a product. So the first thing I can do is use that product property of rule number 4 and expand it into the sum of 2 logs. So this would turn into the log of the first factor, which is x, plus the log of the second factor, which is e to the x. In other words, here's one factor, here's another factor. So I take the log of the first factor plus the log of the second factor. Now the question is can I go any further? In other words, can I expand this any more? It's just ln of x, there's no product here, there's no division, I don't see any property. This is base e, so there's nothing I can do to simplify this piece. Is there anything that I can do using my properties to rewrite this piece? There is something else I can do here. There's a couple things I can think of. I can either bring this x out in front as a multiplier, property number 6, or if I really recognize what's going on here, because if I use property 6, then I'll have to, at that point, use property 2. If I can just see property 2 here right away, I don't even have to use property 6. So think about this. This is an understood base of e, right? So this is a base of e. The base in the argument is e. And then I have an x here, so this is property number 2. This is just going to leave me with whatever this power is. It's just going to leave me with an x. So I believe this says ln of x plus x. This is property 2 that I'm using here. If you don't see that right away, here's another way to think about it. So alternatively, and a lot of these problems have more than one way to do them, just like the exponent simplification had more than one way to do it. Some ways took longer than others, but if you're using the rules properly, it doesn't matter. You just might take a little longer. So the alternative here, so this is my answer. The alternative, so here's where I was. If I didn't see property 2 right away, maybe what I saw was this, property 6. This comes out as a multiplier, so x times the ln of e. But now, hopefully, that is just staring me in the face, telling me about ln of e, understood base of e to what power gives me e back? Ln of e is 1, and x times 1 is x. And so now I get ln of x plus x. Either way I do it, I get down to the same point. I just used the properties a little bit differently depending upon which way I saw first. I have to admit, I often always want to bring this over. It just makes more sense to me. I'm not sure why. And then I just know ln of e is 1, and so then I know exactly what's going on. But if you can see property 2 right away, then go for it. So there's the first one. The second one, let me go, give myself more room here. Boy, I just jumped here right to a nasty looking one. Goodness. So this one, again, they want me to expand it. It's a single log with a lot going on in the argument, and they want me to use those properties to see if I can split it up into a bunch of separate logs. So it's a natural log, so it's understood base is e. The first thing, again, that I notice here is the argument is all raised to a power. So I'm going to bring this power out in front as a multiplier. So I'm going to write 2/3 times the ln of x squared minus 3x plus 2 over x plus 3 squared. So I brought the power out in front as a multiplier. Makes it a little bit easier for me to see what's happening. So now what I notice next is that I have ln of a quotient, which turns it into the ln of the numerator minus the ln of the denominator. So the quotient property, which is property number 5. And this 2/3 is in front of this, so whatever this guy splits up into, the 2/3 is going to be multiplying with, so I'm going to put parentheses because this is going to turn into 2 logs. So it's going to be the ln of the numerator, which is x squared minus 3x plus 2, minus ln of the denominator, which is x plus 3 squared. So ln of the numerator minus ln of the denominator. And I put parentheses around this because it's getting a little complicated with the argument, and I want to make sure I know which argument goes with which ln. So now I'm going to go see if I can split these up anymore or do anything with them. Well, this guy I'm already kind of wanting to do that, and I'm going to in a second. This guy, so we don't have a property for things adding or subtracting in the argument. What we have a property for is the argument where things are dividing or the argument where things are multiplying. So the question is can I factor this? Because if I can factor this, then I will have multiplication going on in the argument. So I'm going to work on that. This is ln of, can I factor this? So easy big X, x minus 2, x minus 1, right? Multiply the 2, add to a -3, needs to be a -2 and a -1. So there's this guy factored, so I decided to factor. And this one, I can write minus, this 2 can come out in front of as a multiplier, ln of x plus 3. So I think this one's done. Okay, this guy is ln of a sum. We don't have any property that says you can split that up. So this guy, I believe, is done. This one's not done yet. So I've got 2/3. This is ln of a product, right? Here's the first factor, here's the second factor, which means I can split this up into the ln of x minus 2, the first factor, plus ln of the second factor, which is x minus 1. And then this guy, I decided was done, minus 2 ln of x plus 3. None of these are like terms. They don't have like arguments, so I can't combine them. And I'm done. I could distribute the 2/3 in front of each one of these. It's probably what the book does in the back of the book. So in other words, I have no problem if you leave it here. The back of the book probably says this, 2/3 ln of x minus 2 plus 2/3 ln of x minus 1. And then you take 2/3 times a -2, so they're going to write minus 4/3 ln of x plus 3. certainly nothing wrong with that answer, but I'm okay if you leave it here because you did what I asked you to do, which was you split it up as much as you possibly could. Let's see, so we've got one more of these where we're being asked to split things up. So number 3. So this is a single log, a bunch going on in that argument, and they want me to try and split it up. So let's see. First thing I see is a quotient, so I'll go ahead and split this up as the ln of the numerator, which is 3x. I'm going to write this properly under here, 5x plus 2, minus ln of x minus 3 to the 4th. So ln of the numerator minus ln of the denominator, because it was a quotient. Now what I'm noticing is that this is a product right here. This is the ln of a product. Here's the first factor. Here's the second factor. So I can split this up into ln of the first factor plus ln of the second factor. So that turns into that. And this one, again, that power I can bring out in front. So minus 4 ln of x minus 3. Again, this one looks done to me. Okay, this is not a product, it's not a quotient, so there's no rule that tells me I can split this up. So I think this piece is done. I need to look at these two pieces. This piece is bothering me because I made a comment, you don't want to leave radicals with logs. If you're trying to use all the properties, this means that this guy is to a power and you need to think about what it is. And this one I know a lot of you will think it's done, but it's not. So this is the ln of a product. This 3 is multiplying with that x. So that means it can go one more shot into ln of the first factor, 3, plus ln of the second factor, which is x. So now this one's bugging me, plus ln of 5x plus 2. So instead of the radical, I'm going to write this as 5x plus 2 to the what power? 1/2 minus 4 ln of x minus 3. Okay, so now these are each done. There's nothing more I can simplify with because it's the base of e, so there's no more properties here. This one has one more shot, and this one I decided was done a while ago. So my final answer here is ln of 3 plus ln of x plus 1/2 ln of 5x plus 2 minus 4 ln of x minus 3. So there it is, all pulled apart using the properties into as many separate logs, adding and subtracting as I can think to do with it. Again, this is not usually the way we go, the direction we go. Normally the direction we like to go is, if we have a bunch of separate logs, condense it back into a single log because it will help us to be able to solve an equation, which is what we're trying to get to eventually. So that's what these next 3 examples are about. So number 4, I've got a bunch of separate logs adding and subtracting. And they want me to condense it into a single log. And actually, they didn't do a very good job because we could have split this up even more, right? ln of x minus ln of x plus 2. ln of x minus 2 minus ln of x. I could have done more on that. And I could have done more on this because this factors into x plus 2, x minus 2, and I could split those apart as well. So they only went halfway. But ultimately they want me to put this into a single log. So I'm taking the properties now, I'm going in reverse, which is, again, typically the way we want to do things anyway. So how do I put these all together? Well, I guess I'll just go from left to right here. I'm going to take these two, since it's 2 separate logs, adding, and they're the same log, same base e, I can condense this into a single log. So I'm going to take these two, condense it into a single log where these two guys are multiplying, right? So in other words, this x over x plus 2 is going to be multiplying with the x minus 2 over x. And then I still have this guy to consider. So I took these two, and they came from the log of a product. I'm going to go do this product and see what happens. So this gives me ln of, these x's cancel. I can't factor, so this is x minus 2 over x plus 2. So there's the first log. And then minus ln of x squared minus 4. So now I have to take these two and condense them into a single log. So take one step at a time, don't try and do too much at once. So what happens when you have two of the same logs, the same bases, that are subtracting? That's the quotient property, and I can condense it into log of an argument that's dividing. So in other words, this is going to condense into ln, so be careful here. This whole thing would be in the numerator, x minus 2, x plus 2, over, this would be in my denominator, x squared minus 4. In other words, x minus 2 over x plus 2 divided by, so here's my big division bar, x squared minus 4. So what's going on here? Complex fraction, right? So you have a couple choices. You can either multiply top and bottom by the LCD, or since it's a single fraction over a single fraction, you could just take them and divide them, which means multiply by the reciprocal. So in other words, what's going on here is I have the ln of x minus 2 over x plus 2 divided by x squared minus 4, which means multiplied by 1 over x squared minus 4. So it's this divided by this, so that means it's this times 1 over this. And now I'm going to try and simplify. So this is what I'm trying to figure out from my argument of the log. Can I simplify this? Well, I need to factor this. So this is x plus 2, x minus 2, right? So can I cancel anything? I can get the x minus 2's to cancel. So that's cool. So I end up with ln of, what's on the top here is a 1, and on the bottom is an x plus a 2 squared. X plus 2 times x plus 2. So now I know you're tempted to leave it like that, but I'm going to tell you to go a little bit further for me. Do not split it up into two separate logs, so don't go that way, but this is 1 over x plus 2 squared, which means that I could actually write that as x plus 2 to what power? So I'm going to unsimplify it and bring it up as a negative power, because we don't have issues with negative powers with logs. So x plus 2 to the negative 2 would be 1 over x plus 2 squared. And to make this look even nicer to look at, I can bring the negative 2 out in front here. ln of x plus 2. This is probably the nicest way to write that as a single log, because in this form it becomes much easier to solve an equation with. So that was a little tricky there at the end. Again, there's different ways to get there. I tried to take a path of least resistance in terms of understanding, but there are different ways to get there. You know, I could have taken this and combined it with this guy first, or these two first, or as long as I'm using the rules properly, I should still end up at this piece right here. So let's see, number 5. I used up all my board space on that one, so let me get rid of this. So notice, simplifying these not only takes the properties of the logs, but it also relies on, can you factor? Do you know how to simplify algebraic fractions, complex fractions, all the stuff in the past, all coming back to kind of haunt us a little bit if we didn't learn it well in the first place. Now we still need to be able to do it. So number 5. Okay, so combine this into a single log. So, I mean, I could go left to right and think about these two and then do that one at the end, which is I think how I'll go ahead and do it. But before I even do that, I don't like this because again, that radical in there messes me up in terms of knowing what to do. So first thing I'm actually going to do is rewrite this 6 log base 2 of 5x minus 3 to the 1/2 power minus log base 2 of 3 over x plus log base 2 of 3. And I'm going to bring this over as a multiplier because it's the only way I'm going to be able to figure things out. That radical is a mess and that fractional power is a mess, but I can use the property 5 or whatever property number it is, I can never remember, 6, to rewrite this. So this 1/2 comes out here as a multiplier, and there's already a multiplier of 6. So what happens when I take 1/2 times 6? I get 3. So this turns into 3 log base 2 of 5x minus 3 minus log base 2 of 3 over x plus log base 2 of 3. Okay, so now I know that. Now what do I do with these two? Am I ready to use the subtraction property with logs here? Not quite, because this number out here is still an issue. In other words, that property number 5, there's no multipliers in front of the logs. So I'm now going to bring this over here as the power. So now I know exactly what the power is. So this says log base 2 of 5x minus 3 cubed minus log base 2 of 3 over x plus log base 2 of 3. So a whole lot of manipulation on that first term just to get it set up so I can use my properties to start to condense things. And again, there's different ways to do this. You could have brought this over right away and had the square root all to the 6th power. And if you understand what that means, that's fine. This kind of splits it out so that you know exactly what it means. So now I'm going to go combine these two. So this turns into log base 2. Since it's subtraction, my 5x minus 3 cubed is on the top. And on the bottom is a 3 over an x plus log base 2 of 3. I need to simplify this. So what happens, this is a complex fraction, but I can just think of it as 5x minus 3 cubed divided by 3 over x, so that means it's actually 5x minus 3 cubed times x over 3. And if you want to skip that step and go to here, that's fine. Just understand it's 5x minus 3 divided by this, so that means it's 5x minus 3 cubed times the reciprocal of this. And then we still have this log base 2 of 3 that we need to consider, but let's go finish this off. This gives me log base 2 of, nothing cancels here, so this is, I'm going to write it with the x first, 5x minus 3 cubed over 3. So that's what I get for the first argument of my log, but I still have plus log base 2 of 3. And now what do? If I have 2 logs adding that are the same bases, I can use that property number 4 or 3, which one is it? Property 4, and put these together as, come up here, log base 2 of x, 5x minus 3 cubed over 3 times 3. And this time something does cancel, my 3's cancel, so my final answer here is log base 2 of x, 5x minus 3 cubed. There it is, single log, which makes it easier for me to solve a log equation. Manipulated that mess into this single log right here, log base 2 of x times 5x minus 3 cubed. And then the last one, number 6. Do I have enough room here? We'll see. I'm hoping that some of you get really good at this. And can kind of see where the pieces go. In hard to tell. So this one, they want me to condense this into a single log. They're all log base 3s. I always check for that because otherwise the properties aren't going to work. All right, so let me take these two first, but before I can put these two together as a quotient, I need to deal with the numbers in front of them. So I rewrite log base 3 of x plus 2 to the 5th power minus log base 3 of x plus 1 to the 3rd power, and this guy's okay, log base 3 of x minus 2. So I brought my product, my multiplier, over back into the argument as a power. Now I can put these two together. So this is going to be log base 3. They're subtracting, so the x plus 2 to the 5th will be on the top, and the x plus 1 to the 3rd will be on the bottom. This guy divided by this guy. So it's not a complex fraction, that's nice. And in fact, I can't cancel anything either because there's no common factors. And now I still have minus log base 3 of x minus 2. So now what happens? I've got log base 3. It's minus, right? So it's going to be the x plus 2 to the 5th, x plus 1 to the 3rd, divided by x minus 2. So I'm going to, instead of writing a complex fraction, I'm going to go ahead and think about what it means. So it's this divided by x minus 2, which means it's this times 1 over x minus 2, which leaves me with log base 3. Nothing cancels, so I'm going to have in the numerator x plus 2 to the 5th, and in the denominator I'm going to have an x minus a 2 and then an x plus a 1 cubed. Notice I wrote those in a different order just because it looks nicer. You could have written x plus 1 cubed and then parentheses x minus 2, but I chose to write it this way. There's my final answer. Single log, easier to deal with if I'm trying to solve a log equation. Take a look at this to here. Notice this is a positive log. So the x plus 2 to the 5th ended up in the numerator. Notice this is a negative log. So the x plus 1 to the 3rd power ended up in the denominator. Notice this is a negative log. So the x minus 2 ended up in the denominator. If you can see that on simpler ones like this and jump to here, that can be a real time saver in some instances. I know most of you won't want to do that, but you can kind of see what's going on. Positive logs, that piece will be in the numerator of the new single log, and if it's negative logs, those pieces will be in the denominator. Okay, so I have two more examples here, which is just using the change of base theorem with your calculator to get you used to it as well. And it says, use the change of base theorem to evaluate, round your answer to 3 decimal places. So they actually want me to use my calculator here, and they want me to evaluate log base 1/2 of 15. And the fact is that I can't put it into my calculator that way because the LOG key is base 10. And of course, I forgot to bring my darn calculator, but I have the answers here. So here's the deal. How do I do this? If I want to try and get an approximate answer for this, is I'm going to use the change of base theorem so I'm able to put it into my calculator. So in other words, I can either write this as log of 15 over log of 1/2 and put that in my calculator using the LOG key base 10, or I could, in other words, it's also equal to ln of 15 over ln of 1/2 in my calculator. So usually what I do is I have half the class use your LOG key, and I have the other half use the ln key, and we both get the same answer as long as we're consistent with how we rewrite this. So if we're going to use the LOG key, it's LOG of this guy over LOG of this guy. If we're using the ln key, it's ln of 15 over ln of 1/2. And either way, when you put that into your calculator, you get that, and if I round it to 3 decimal places, it's approximately equal to 3.907 negative. Oops, can't see my own writing here. It's approximately equal to negative 3.907. So you should get that no matter which way you do it, you should get the same answer. And it's your choice as to which way you want to do it. And the second one, they want me to evaluate log base pi of the square root of 2. So again, I can either rewrite this as log base 10 of the square root of 2 over log base 10 of pi, or I could write it as ln of the square root of 2 over ln of pi. Either way. Either way. And there is a pi key on your calculator, so you need to go look for that. It's not a second key. It's not above. It's actually on the key. And you hopefully already know how to put a square root in there. So I should be able to calculate log of square root of 2 over log of pi using the LOG key, or if I want to use the LN key, I can do it this way. And either way I do it, if I round it to 3 decimal places, this ends up being 0.303. So check it on your calculator and make sure that you know how to get there. Alright, so just remember to close the parentheses on the arguments. If you don't do that, you're going to get some crazy answers. So respect those order of operations, I guess is what I'm saying. So that's 6.5. We're ready to go take a look at 6.6. So let me go grab that paper. And get rid of what's on the board. So 6.6 is actually solving log and exponential equations. And we've already done some solving of exponential equations and some solving of log equations as well. We had one way for each one, actually. But before we go over, there's actually 2 ways that I'm going to introduce now. The one we already know about, and then an extra one for each type of equation. But before we do that, there's one more property of logarithms that I want to look at, and it's related to that property of exponents. It says if you have same bases equal, then you can drop the base and equate the powers. Well, the same thing kind of occurs with logarithms as well. So in other words, if I have 2 logs that are equal, that have the same bases, then their arguments must be equal to each other. It only makes sense. If I have log base 10 of x and it's equal to log base 10 of y, then the arguments must be the same. The x must equal the y. That's kind of like where I had a to the u equals a to the v, so therefore u must equal v. If I have same bases equal, then the powers must be equal. If I have same logs with the same bases equal, then the arguments must be equal. And it works in both directions. In other words, if I have a statement between 2 terms and I'm saying they're equal, then I can put a log of the same base in front of each one and still say they're equal. So I can go in this direction as well. And with logs, we actually go a lot in both directions, whereas with the powers, usually we like to get same bases and then drop the base and equate the powers. So an extra very powerful rule to use for logs. So now we're going to review and add an extra way of solving exponential equations. So to solve exponential equations, we can do what we've already done, which is try to make the same bases and then drop the base and equate the powers. So number one method we've already learned. The second method for solving exponential equations is what if you can't make same bases? For instance, so exponential, one way is create same bases. We already learned this, Process number two is what if you can't make same bases? So if you can't create same bases, then what do? We were always able to create same bases. But if you can't, for example, if I have 2 to the x is equal to 5, I have a problem here. This is exponential. The base here is 2. Can I create a base of 2 with the 5? No, I can't. So then what do? So the process here says, if you can't make same bases, like in this problem, then you're going to get one term on each side, just the way it's written, actually. And you're going to take the log or the ln of both sides. In other words, I'm going to introduce, this is what I have, I'm going to introduce a log in front of each one of these, either log or ln. I usually put an log in there when there's no e's, and if I see an e in the problem, then I'll use an ln. So then we will introduce a log on each side. Property above. Working from here to here, going to the left and using this property. So this way is new. This way we already know how to do. In terms of solving log equations, we're going to skip one for a minute and look at number 2. Number 2 says if not all the terms are logs, then get the single log on the left and get the terms without logs on the right, term or terms without logs on the right, on the other side, and rewrite it in exponential form. And then rewrite in its equivalent exponential form and solve it. We've done this. So this we already learned. If I have a single log and terms that don't have logs in them, then I can always rewrite that as the base of the log to the power of the answer equals the argument of the log. We already have done that. So that we've done already. That's if not all the terms are logs. So if I just can make a single log on one side and terms without logs on the other side, then I can rewrite it. What we haven't done is, what if all the terms are logs? I've got nothing but logs. I have no terms that don't have logs in them. So if all the terms are logs, so this is number 1. So if all terms are logs, then what we can do is we can combine them, condense them, so we have a single log on the left side and a single log on the right side, and then I can use this property, drop the logs, and equate the arguments. So combine to get a single log on each side, drop the logs, and equate the arguments. All terms are logs, single, get it? So it's a single log equals a single log. Use the property above, and equate arguments and solve it. So this way is the new way now. So we actually have 2 ways to solve exponential equations now. One that we already know how to do and one that's new that we'll practice. And 2 ways to solve log equations. One we already know how to do and one that we're going to practice. And we may practice all of them. We'll see. I've got 7 examples here. So let's go take a look at these and see what we can do with them. And again, if it is a log equation, then I need, if the original equation is a log equation, then I need to be careful about the argument and the base. In other words, where is the x, where's the unknown, and what are the restrictions that I have to pay attention to. base of a log has to be greater than 0, not equal to 1. The argument of a log has to be greater than 0. So I have to keep that in mind if the original is a log equation. So these say, the directions for these 7 problems are solve, give me the exact answer, and round to 3 decimal places if it's an irrational answer. So I want an exact answer, and then if it's something that, you know, leaves me hanging with, I have no idea what value that is, then I will take it and round it to 3 decimal places as well. So exact answer and rounded answer if necessary. So this first one, looks like this. Base 3 of 3x minus 1 equals 2. They want me to solve this. So I look to see what kind of an equation it is. It is a log equation. So if it's a log equation, there's 2 types of log equations. Either all the terms are logs, or some of the terms are logs and some of them aren't, in which case I'll get a single log on one side and terms on the other side, or if they're all logs, I'll get a single log on each side and then drop the logs. So are all these terms logs? Here's one term, here's the other term. Does this have a log in front of it? No. So this is not one of my new ways, actually. This is one that we've already learned how to solve. The fact is that there's a single log here, and then terms without logs over here. Since this is already a single log, how nice of them, I don't have to condense it. I can just now rewrite this in exponential form. So when I rewrite this in exponential form, so this is nothing new, we've done this before. We take 3 to the power of 2, has to equal the argument, which is 3x minus 1. The question is what kind of an equation is it now? It's linear, so I can do this. This says 9 equals 3x minus 1. I'll add 1, I'll get 10 equals 3x. I'll divide by 3. I'll get x equals 10/3. I know what that is. You don't need to approximate that for me. We'll leave it with the exact answer. Should I be circling this yet, or should I be thinking about things? So this original equation was a log equation, right? The base I knew, so I don't have to worry about that. It's the argument that's the issue. So you must check, and you have to show me that you are checking, because if you don't check, then I don't know if you just forgot to check or if you checked it in your head. You have to show me, I'm checking this. So we need to check that the argument is greater than 0. And the argument here is 3x minus 1, which needs to be greater than 0, not just x. So, you know, some of you might go, oh, I did check. It was a positive answer. We're good. No, it depends on what's going on in the argument. Even though you have a positive answer here, if the argument does something to that positive answer and turns it into a negative answer, you have an issue. So I need to put this in here and make sure. So if I take 3 times x, which is 10/3, and then subtract 1, am I still going to be greater than 0? Well, actually I am, because the 3's will cancel. I'll get 10, and 10 minus 1 is 9, and 9 is greater than 0. So we are good, and I can circle it. But you need to show me that you did that and that it worked, or didn't work, as the case may be. So that's a review of something we've already done. Number 2. Okay, so number 2 is, what kind of an equation? Exponential. So nothing I have to worry about in terms of restrictions, but now I have to think about how I solve an exponential equation. So this is exponential, and I'd like to try and create same bases, because if I can, it's usually easier. And right now, this is confusing because I have a base of 4, but then I have this extra multiplier out here of a 3. So can I turn that into 12? I hope you tell me no. The base here is 4. I'm not multiplying same bases and keeping the base and adding the powers. This is a completely different base, but it's in the way in order for me to think about creating same bases. So how do I get rid of the 3? We did one like this. We're going to divide by 3. So I divide both sides by 3. So that gets rid of that 3, and I have a base to a power over here. And on this side, it's 2/3. So now, still exponential, but easier to look at. The base here is 4. The base here is 2/3. Am I going to be able to turn these into the same bases? The only thing I can turn 4 into is a base of 2, and 2/3 can't turn into either a base of 2 or a base of 4. So now I'm stuck. In the past, I wouldn't know what to do to solve this because I can't create same bases. But now we have a way to deal with this in terms of, since I can't create same bases, I'm going to actually take these two and introduce a log. What log will I introduce? I'm going to introduce a log that I can use on my calculator. So I'm either going to introduce log base 10 or I'm going to introduce ln, which is a log base e. Again, I usually don't introduce an ln unless if I see an e in the problem because it might make life easier, but I don't, so I'm just going to introduce log base 10. Can I introduce ln? Sure, we'll get the same answer in the long run, but that's usually the way I do it. If it's numbers, then I'll introduce an log base 10. If it's an e, which is also a number but a special number, then I'll introduce an ln. So I'm going to introduce an log base 10 in front of this guy. So I'm going to have log base 10 of 4 to the 2x equals log base 10 of 2/3. And now you're looking at me like, well, how did that make life easier? It looks even harder now. Well, not really, because what it's going to allow me to do is to turn this into an equation that's linear in nature. And here's how. So the property that says if you have a log of an argument that's to a power, property, I forget what number, 6, I can now bring this out as a multiplier. So I can rewrite this side as 2x times the log of 4 equals the log of 2/3. The unknown here now is right here, and this is now a linear equation. Yes, it's a log equation, but not really, because I know you see logs, but these logs are just numbers. These are constants. It's a linear equation. So all I have to do is solve for x. Well, what's going on over here? If this just said 2x, you would tell me to divide both sides by 2, right? Well, there's a little more multiplication here. This is a 2 times the x times the log 4. The log 4 and the 2 are numbers. The fact is that they're the coefficients of the x, so I'm going to divide by 2 times log of 4, which means I'll divide this side by 2 times log of 4. The 2, this is all multiplication here. The 2's cancel, the log of 4's cancel. I'm left with just an x on the left side. And over here on the right side, what a mess. I've got a log of 2/3 over 2 times the log of 4. This is my exact answer. This is solved for x. This is just a constant over here. I have no idea what that constant is because it's hard for me to approximate it in my head, but this is the exact answer right here. This is one where we want to go and get an approximate answer, and we'll round it to 3 decimal places. So here's where the issue comes in. How do I get that into my calculator? Very carefully. You can manipulate a little bit. So this log of 2/3 doesn't really need manipulated. You could turn 2 times the log of 4 into what? Or, let's see, x is equal to log of 2/3. I'm not going to turn that into log of 2 minus log of 3. That just makes it harder. On the bottom, though, this multiplier can come over here as a power. So this is log of 4 squared, which is 16. That might be easier to put in your calculator. Either way, in terms of the approximate, when you put this into your calculator, so here's calculator, you're going to type log, parenthesis comes up, 2, and then you do divided by 3, close the parenthesis, divided by, here's where the issue comes in. You type in 2 log, parenthesis 4, parenthesis, you know I'm being so good, I'm remembering to close my argument in parentheses. The calculator uses order of operations. What is it going to do and what order will it do it in? It'll figure out 2 divided by 3, so it'll have this log's argument. And then what it sees is a divided by 2 and it times the log of 4. So it's going to do log of 2/3. and then it's going to take that answer and divide it by 2, and then it's going to take that answer and multiply it by the log of 4. You don't want this being multiplied by the log of 4. The log of 4 is part of the division, so you're going to have to put an extra set of parentheses around that to tell it to do that. That's why this form's a little easier, because this form in the calculator, you can just put in log of 2 divided by 3 in parentheses, and then divided by log of parentheses 16. It will respect order of operations here because there's just the one division, there's not this extra timesing here. It's going to figure this out, and then it's going to divide it by this. But anyway, either way, just be very careful that you understand sometimes you have to put extra sets of parentheses in. If I do that and put it in my calculator and I rounded it to 3 decimal places, this guy gave me approximately equal to negative 0.146. So for your checking and making sure you can use your calculator correctly, there's the approximate answer for that one, negative 0.146 rounded to 3 decimal places. So that's where exact answers and approximate answers come in handy, where my exact answer has a bunch of logs in it, and then I want to get an approximate for it. So let's go take a look at number 3. Are you having fun yet? I heard a bunch of yeses. We love this. Let's do more, right? Yeah? No? Yes. So number 3 is 3. I'm getting bored. Is 3 to the x equals 10. I kept hoping that we'd eventually get back to class, but obviously we're not going to. So you're stuck with me like this, and I'm stuck looking at my bike and the hose and things like that, and ladders. So here we go. Number 3, 3 to the x equals 10. They want me to solve it. What kind of an equation is it? It's exponential. So how do I solve an exponential equation? I have 2 ways. Either try to create same bases, or if I can't create same bases, then I'll introduce a log on either side. So I know what the base here is. It's 3. The base here is 10. Can I create same bases? Can I turn 10 into a base of 3? Or can I turn them both into the same base? No. So I can't create same bases, which means that I have no other choice but to try to introduce a log on both sides, since I have 2 terms equal to each other. So I'm going to introduce log, and I'm going to introduce log base 10 again because, again, I don't have an e in this problem, and log base 10 might help me because I do kind of notice a 10 sitting there. So I'm going to write log base 10 of 3 to the x equals log base 10 of 10. So I'm introducing log base 10. Again, I know you go, how does this help? It always helps because remember the unknown was in the exponent, and when I put a log in front of it, the exponent could come out as a multiplier. So I can rewrite this side is x times log of 3 equals, and now think about this side for a moment. What is log of 10? Remember, this is log base 10. It's 1, right? Because 10 to the first equals 10, so this is 1, which is kind of nice. It made my life a little easier by introducing that log base 10 instead of ln, which is log base e. So what kind of an equation is this? It's linear. I know it has a log in it, but the log is just a constant. The equation where the unknown is, it's linear. So all I have to do to solve for x, that x is multiplying with the log of 3, so I just need to divide by log of 3. So divide both sides by log of 3. This is x equals 1 divided by log of 3. This is my exact answer. It's meaningless again, so this is where I would ask for an approximate answer, and if I round it to 3 decimal places, so there's 2 ways you can do this. You can figure out log of 3 and then hit the x to the negative 1 key, which is just the reciprocal, or you can do 1 divided by log of 3. And either way you do that, you should end up with, for the approximate answer to 3 decimal places, of 2.096. So this is my approximate answer, 2.096. So number 4. Number 4, again, the directions are solve, and what I see there is a log equation. So the question is are all the terms logs? Because if all the terms are logs, I will get a single log on each side and drop the logs, the new property. If all the terms are not logs, then I will get a single log on one side, the terms that don't have logs in them on the other side, and do what we did before, which is rewrite it in exponential form. So that's the first decision. Are they all logs or not? So log, log, not. So since they're not all logs, that means I'm going to do the way I used to do, which is single log on one side, not log on the other side, and then rewrite in exponential form. But this is not a single log on this side. So here's where those properties come in handy, where I told you normally what we do is we condense into a single log, and this is the perfect example. I'm going to take this and condense it into a single log so that I can then rewrite it in exponential form. So as a single log, these two logs are adding. There's no multipliers in front, so I don't have to worry about that. So this can condense into the single log, log base 6 of this x plus 4 is going to be doing what with the x plus 3? Multiplying, and that equals 1. So this is what I need to figure out now. A new marker here. So single log equal constant that doesn't have a log in it. So I will rewrite this in exponential form. So this becomes 6 to the power of 1 has to equal x plus 4 times x plus 3. So what kind of an equation is this? Ultimately, it looks like it's going to be quadratic. And 6 to the 1, of course, is just 6. But here's where mistakes get made. And I noticed this on a quiz somewhere online. Don't pull this apart and say that either x plus 4 equals 6 or x plus 3 equals 6. We don't have a rule that says you can do that. That's not the zero factor property. The zero factor property says you can pull them apart if there's a 0 over here, but there's not a 0 over here. So I'm going to need to multiply this out and bring the 6 over to get a 0 over here and then proceed with that property, or the quadratic formula, or maybe the square root property if it ends up looking like it will work even better. But bottom line is I need to multiply this out. This is 6. This gives me x squared plus, what will my middle term be? 3x and 4x, so 7x, and then plus 12. And now it's quadratic. I'm going to get the 6 over here. So I've got 0 equals x squared plus 7x plus 6. Now I'll use that zero factor property and try and factor this. This is the easy big X. There's no GCF. 0 equals, multiply to 6, add to 7 is going to give me x plus 6 times x plus 1. There's the x squared plus 1 plus 6 is 7 plus 6 times 1 is 6. Which gives me two answers, x equals negative 6 or x equals negative 1. So now, I'm tempted to circle them, but what do I need to remember to think about? This was a log equation, right? And the base we knew is the argument where the x was, so the argument is the issue, so I must check the argument greater than 0. So I know some of you look at me, oh, they're both gone, they're both negative. Not necessarily. It depends on what the arguments say. The fact is, though, I have two different arguments here, so I'm going to have to check both of them. If one of them fails, then it doesn't matter about the other one. So if there's an issue with either one of these, that answer's gone. So I need to check argument greater than 0. So let's grab negative 6. So I put negative 6 into, so in other words, the argument here is x plus 4 greater than 0, but also I have to check x plus 3 greater than 0. I've got two arguments to check. So let's put negative 6 in. If I put negative 6 in here, is negative 6 plus 4 greater than 0? No. I don't even need to check that one. The fact that it fails in the first one means you're trying to take a log of a negative, and that isn't going to work. This guy's gone. So now I'm going to check. So this was me checking negative 6. So now I'm going to go check negative 1. So negative 1 plus 4 greater than 0. That one does work, okay? But you got to check the other one too, but also x plus 3, so negative 1 plus 3. Is that okay as well? Because it has to work in everything. You can't have logs of negatives anywhere. That one also works, so guess what? Even though it's negative, it works because when I put it in the expression for the argument is positive. It's greater than 0. So there's my only solution to that one, x equals negative 1. All right, so now we're ready for number 5. So this one, I see a log equation. So the question is, every term logs, or are some of the terms not logs? So log, not a log, log. So I see not all logs, which means I'm going to put logs on one side, terms without logs on the other side, and then create a single log. So I'm going to take this log and shift them over here. So this left side becomes log of 2x minus the log of x minus 3 equals 1. So I subtract this, I moved them to the other side. So now create a single log. So to create a single log between these two, they're subtracting. So as a single log, this is single log of 2x over x minus 3 equals 1. So there's my single log equal to a term that doesn't have a log in it. So now I'm going to rewrite it in exponential form. Oh, what's the base here? What's the understood base here? 10. So write it in if you need to see it. So 10 to the power of 1 has to equal the argument, which is 2x over x minus 3. And 10 to the power of 1 is 10, right? So there's my equation. 10 equals 2x over x minus 3. What kind of an equation is that? Well, I'm not sure linear, quadratic, but what I am sure of is that it is a rational equation. In other words, there are fractions here, and there are issues with this guy. X can't equal 3, right? But you know what? It can't equal 3 here either, so I don't need to worry too much about that because I'm going to have to check my restrictions at the end anyway. How do I deal with this? I'm going to clear the fractions, which means I'm going to multiply both sides by x minus 3 times x minus 3. Well, on the right side, the whole point of that was to get these to cancel. I just get 2x. On the left side, nothing cancels, so I need to distribute the 10. So I'll get 10x minus 30. What kind of equation is this? It's linear. So I'm going to, I guess I'll, I'm not sure how you want me to do this, but maybe I'll just play with you. I'm going to subtract 10x here. I'm putting my x's on the right side. So I get negative 30 equals, this is going to give me negative 8x. So I'm creating a lot of negatives here. And then I'm going to divide by negative 8, divide by negative 8. So I get x equals, this turns into positive, and I can simplify this at least by 2, so 15 over 4. So x is 15/4. Before I circle that, even though it's positive, before I circle that, I remember this was a log equation, so I'm going to have to check the arguments. So let's see, check argument greater than 0. And there are two arguments here. One of them is 2x greater than 0. Also, x minus 3 needs to be greater than 0. They both need to work. My answer is 15/4. So if I take 2 times 15/4, will I be greater than 0? Yes. I don't even need to figure out it's two positives, and so I'll get a positive. Also, if I take 15/4 minus 3, will I be greater than 0? So even though it works here, if it doesn't work here, then it's gone. So let's see. If I take 15/4, let me turn that into a mixed number. That's 3 and the operative word there, and 3 3/4, right? So this is okay. This will be greater than 0, so I can go ahead and circle this as my answer to that problem. X is equal to 15/4. Let's go take a peek at number 6. Start it here. So there are a variety of ways to do this one. When I see this, I see a log equation, and I see that every term is a log. So I would kind of like to use the new rule, which says if I have 2 logs equal, I can drop the logs and just equate the arguments. But the fact is, in order to use that rule, I can't have that 2 there, and I can't have that negative there. It has to be log something equals log something. They both have the same basis, so that's good. So I have a little bit of manipulation to do if I do it that way. Otherwise, I could bring this log over here, add it, and set it equal to 0, write as a single log, and then rewrite in exponential form. So I'm going to try the new way, because this is a log equal to a log. I just have to write it so there's no numbers other than a 1 in front of this. So tell me which property, what does the property do to this? This 2 can come in here as a power on that x, on that argument. And this negative, log base 4, can come in here as a power on this argument. What would my power be? Negative 1. So this says log base 4 of x squared equals log base 4 of 9 to the negative 1 power. Now I can use my new property and drop the logs and equate the arguments. Drop logs, equate arguments. So this says x squared equals 9 to the negative 1. How nice is that? This argument equals this argument. This is quadratic. I'm just going to rewrite what this says. So x squared equals, what is 9 to the negative 1? 1 over 9. How many answers am I going to get? 2. What's the easiest way to do this? Square root property. Square root plus or minus square root. So x is equal to plus or minus. The square root of 1/9 happens to be 1/3. So I get 2 answers here. X is positive 1/3 or x is negative 1/3. What kind of an equation was this? It was a log equation, and the unknown was just in this argument right here, right? So again, I must check argument greater than 0. There's only one argument to check, and the argument is x. Oh, that's really nice. So I've got 2 answers here. One of them is 1/3 greater than 0, yes. The other one is negative 1/3 greater than 0, no. So this guy's gone, right? So only x equal to 1/3 is my answer on this one. So I think I'm out of time. I didn't quite get to my favorite one in this section, which is number 7. So next Tuesday, we'll work on number 7, and then we'll move on to section 6-7 and 6-8 probably. What else you should be doing for Tuesday is that quiz. So don't forget that the quiz is due again in the email that comes out with the handouts for this lesson and with the link to the YouTube video. We'll also remind you of your deadline on Tuesday for that quiz. So have a good weekend, and I'll see you again next Tuesday.